Morning, everyone. Welcome back to Math 53. So today we'll start our last topic of the course, which is the vector fields and calculus with vector fields. And yeah, so we'll do this over this week and part of the next week. So in the next week we have a final. So I apologize for not telling you that sooner. I had some trouble understanding what the department wants with those finals. So the final for the course will be on the last day of classes, right? So which means it's Friday, August 14th. So the schedule for the last week will be unusual. It will not be like all other weeks. So Friday the 14th. And the final will be administered via Gradescope, same way as all the tests we had so far. So I'll make a separate announcement about that. So it will be a longer test, right? So it will be given 4 hours to complete it, including submission of the problems. And you will be given, as usual, a 24-hour window. So I'll post an announcement for this today over on V courses. And if some of you have any logistical issues that due to some reason you cannot be doing this final over the 24-hour window between, so I'll specify the exact time, but I think we can put it 10 a.m. or 10 a.m. to 10 a.m. So 10 a.m. on Friday through 10 a.m. On Saturday. And within this 24-hour window, we need to do the test. So I saw some of you were complaining about having too many finals in one day. So I know that some of you having finals on Thursday. Some of you have other finals. So if there is some problem, please let me know. I hope there won't be, right? So since, it's a summer session, we don't expect to have too many problems. But yeah, anyway, if there is a problem, let me know. Now the remaining quizzes, so we'll have quiz on this week, right? So there will be quiz number 5, usually on Thursday. Which is what? It's the 6th. So that goes in usual format. There will be a special announcement, and then there will be a small quiz on not small. It will be just a regular quiz on the next week about the content of section 16, right? Of the vector fields, and that will be done. So Thursday next week will be a review session, and instead we'll have the quiz on Wednesday on the 12th. Okay, so that's quiz number 4, which covers the materials of section 16. And we'll start working on that today. Okay, and then what else? And then the review will be done on Thursday. The 13th. Review of the entire course. Yeah. So yeah, during this week we'll cover the material. Well, this week and Monday maybe next week we'll cover the material of the of section 16, and then we'll have test on that, the quiz on that next Wednesday, And then Thursday we do the review, and Friday we have the final. So that's the plan for the last 2 weeks. So I put weeks 6 and 7. Actually, I think it's wrong, right? Nobody corrected me. 7 and 8. Right. Our term is 8 weeks in summer. Okay. Any questions? Ruben emailed me yesterday and said that he's about to post them. He was just checking that all students have taken the midterm. I think he's almost done. That is correct. The 2 lowest quizzes will be dropped. Yes. So once I get all your quizzes in, I can I just take out the 2 lowest ones and then use the others to calculate. So yeah, so we have 6 quizzes overall, right? So 4 best quizzes out of 6 will be taken into account. Yeah, so about that, is everything curving? Well, I'll look at the grades in the very end. So it definitely makes no sense to curve any grades in between, say quiz grades or midterm grades. So typically, so personally, I don't like the idea of the curve, right? Because it's some students suffer so sometimes the way the curve works, it's not favorable for students with better grades. So typically, if I see that a student is on the boundary between 2 grade brackets, right? So say you have, say, B plus, so say B starts from 80%, then you get 79.6. Usually I just bump the student to the next category. Yeah, so I prefer doing those kind of things as opposed to the curve. And after all, this is Berkeley, right? So we should not use curves. We should even if we're sitting at our homes. By the way, guys, what percentage corresponds to an A in the class? So yeah, so typically I start off with a 90% plus, and then if I see that that's too strict, then I relinquish that a little bit, and I move it a little bit to the left. Yeah, so like so yeah, so think about it. If you have 90+%, then you are guaranteed an A. And then A minus, yeah, so maybe A minus will be, yeah, so there will be pluses and minuses, and perhaps A minus could be like 88, 87 and a half, something like that. Yeah, so that's a possibility. Right. Okay, now let's continue. So our story for today is the vector calculus. It's everything like vector calculus. Let's start with vector fields. Right. So remember, I told you in the very first lecture what is a vector, right? So a vector was what? So can somebody remind us what a vector is? So there's a vector u here. So remember, we saw the subtlety was that it's not just one segment, one directed segment, rather it was a set of all directed segments of equal length, which are parallel to each other, which means that you can point, you put a, in every point of the space, have, well, they're meant to be equal length, those vectors that I draw here. So it's the same vector, which sort of the same directed segment, which starts from every point of the space. So we call this a vector. And so this definition was convenient because if you want to say add vectors, we need to be able to move them, tail of one vector to the tip of another, so that we can add them, right? Using either triangular rule or the parallelogram rule. So the idea of a vector field is a generalization of that, right? So essentially, this setup here is also a vector field, and this is so-called constant vector field. So vector, aka constant vector field. And what is, well, vector field in general? It's the following things. Let me first explain it, and then I'll write the definition. And now you imagine, so in other words, how to make it non-constant, right? Well, what you do is just you take every point in space and then assign a vector to it. So there's a vector, so every point x, y has a vector, say f, which depends on that point. And every point has a unique vector, right? So say this is x1, y1, and this is x2, y2, and then we have f of x2, y2. So here f will be a vector function which does the following. So it's a vector field f. You should think of it as a map from, let me formulate it in generality for n-dimensional Euclidean space. So it's from Rn to Rn, but these Rn's are treated differently, right? So the first Rn is treated as a set of points, right? And the second one is treated as a vector function, right? So it gives you the vector f of x1 through xn, which is a vector in some n-dimensional space. Yeah, so this is the vector field. So it's a rule that assigns to a point in Rn an n-dimensional vector f, which depends on x1 through xn. Right. So the word field here sort of designates the fact that this vector depends on the choice of coordinate. So it's a terminology that used a lot in physics, right? So, for example, we'll talk about this later, right? So, for example, gravitational field, right, or electric field, and so you will know how to write formula for it, and it shows you that the well, it's how this vector behaves as you move around in space. Okay, so that is vector field. So think of a field. You can replace field with vector function of coordinates. So it's vector valued. Yeah, so it's got a, and then as opposed to say scalar field, right? So in physics, you can also have scalar fields, which is just, a function of coordinates, right? It's just another fancy way to say that, it's a function from, say, Rn to R, right? That takes you coordinates x1 through xn, just to this function x1 to xn. So just a fancy name for function of n variables. But look, yeah, in sort of in this physics terminology, it's called field. Okay, so let's look at some examples. So we already had the first example, the constant vector field. Okay, so let's write it down. Constant field, we'll just call it U. Yeah, without any dependence. So for simplicity, let me draw it in two-dimensional space. So it takes every point and then assigns it the same vector. So it's a vector constant, right? Like, for example, in example with the Kepler motion, angular momentum was a vector constant. So it looks like this. Okay, next example, this is so-called Euler vector field. So let me just write the formula, and then you can tell me how, you can try to describe how it looks like. So let's say it's vector v of x. Now let's take it, let me write it in full generality here. So it's v, so let x be, so to make the shorthand notation, so x1 through xn is just a vector, garage door. Yeah, so so v of x, which looks like x. So let's do two examples. Let's do x, and then let's do x divided by absolute value of x. So can you describe how it looks like in words? What is the pattern? So it could be easier to look at some two-dimensional example, right? So you say x is a two-vector. Or three-vector. Let's say let's try to draw it in 3 dimensions, both of them. So it's the same with graphing of functions, right? So you can just put several points in space and then just draw it. So I think that maybe some notational subtlety here is that this x here is a bit different than that one, right? So this vector x simply denotes the tuple of the point in space, and vector on the right denotes the actual vector that is placed at that position. but I mean, it's the same, they have the same meaning, right? So we talked about this, right? So that there's a one-to-one correspondence between Rn as a set of points and Rn as a vector space, as a set of vectors. You know, you can add vectors, you can add points component-wise. How does this field look like? What do you think? Vector pointing away from origin, well, rather plurals, like it's a bunch of vectors, many vectors. So indeed, so because what it shows that you pick every point x, right, in space, and the rule says that you attach a vector with components which are equal to the coordinates of that point, right? So yeah, so sphere. Okay, so I think when you say sphere, you mean okay, we'll get that, right? So say if this point has coordinates x1, x2, x3, right? So then we should attach a vector here to this point with the same coordinates, right? And of course, well, it should go. It should belong to the ray, to the line that goes through the origin, right? So in this point we have here, for example, let's take point 1, 0, 0, right? It's the point over here. And according to our rule, we should attach vector whose coordinates are equal to 1, 0, 0, right? So it will be a vector which points in the x direction, right? So same, if you pick a point 0, 1, 0, this point will have a vector attached in the y direction, and so on, right? So, so what will it look like, right? It looks like, you know, at every point we have a vector that points in the direction, you know, away from the origin, and the length of the vector is proportional to the distance. Well, it's equal rather to the distance of this point from this point to the origin, right? So the farther you go, the longer is the vector. So for example, you take point 0, 2, 0, the vector will be twice longer. And so as you go to infinity, those vectors become longer and longer. Okay. Yeah. So sometimes it's called Euler vector field. So it's really like, so I think so Alex mentioned the sphere. So what's the role of the sphere here? So you can draw a sphere of any radius, right? And then those vectors, they will be piercing through the sphere. You know, they will be orthogonal to tangent planes to the sphere. Yeah. So that's right. So of course it's may look a little bit unphysical, right? So that it goes as you get moves to infinity, it increases in magnitude. So let's look at this guy. Let's normalize it. So we take at every point x, we take a vector with coordinates x, and then we divide by the length of the vector x, right? So in this case, you'll have a unit vector which looks in the same direction here. So this vector field, it has, you know, it's a unit vector in direction of x. Yeah. Of course, so actual physics example of this field, for example, would be electric field from a point charge, right? So electric field from charge q, say it's positive, right? So Yeah, I'm not sure which system of units you used in your introphysics class. So let me use the so-called CGS system, which does not include any 4 pi's or epsilons or anything. So there's the coefficient, there's the coefficient k here, which is actually scaled to 1, right? So this coefficient, whatever it is, it can be scaled to 1. So the field is equal to Q times X, right? And then divided by absolute value of X in which power? 2, or so remember, I put X 3, that's right. Yeah. So the reason why it's 3 is because you can write it as Q over absolute value of X squared. So that will be the magnitude, right? And then if you actually talk about direction, you need to multiply it by the unit vector in x's direction. And so yeah, this is the famous formula, Q divided by R squared. Yeah. So of course, because of this 1 over R squared, the absolute value of this vector rather decreases as x goes to as you move away from the charge, so that the total energy that is contained by the electric field of the charge is finite, right? So you can integrate that to find energy. And so yeah. Okay, so we talked about electric field. Now let's talk about magnetic field. So the canonical example would be to take a current that flows along a vertical piece of wire. And then, sort of in typical physics setting, you would put some metal chips on a plane, and then you'll see that they form this pattern with concentric circles, right? So, and then depending on which way the current goes, right? So we should use again that as a right-hand rule kind of thing, right? So one of them is to put a thumb along the current, and then the four fingers would curl along the direction of the vector of the magnetic field. The magnetic field B will look like this, right? So it will be directed along the tangent lines yeah, so be directed along the tangent lines to the circles, and then yeah. So let's not try to figure out the coefficient now, but let's just try to write the formula. So B now is a vector field in x and y plane, which is here. Right. So how can we write it down? Right. So we have a so first let's see what happens. Let's pick a circle of radius r. Or yes, let's say there's radius r here, and then we want to write a formula. So we want to so then the so it will be the vector which has some x component and some y component, and the x component should be proportional. So if you wanted to curl in the counterclockwise direction, as it's shown here, right? So then it would look like it's minus y, comma x, and then it can multiply some function some scalar function of absolute value of x. Well, let's not call it phi. In fact, we should know. So let's say there's some coefficient alpha, which depends on the current, and then divide by absolute value of x. Now, to which power should we put it, right? So how quickly the magnetic field decays as you move away from the current. So it should be weaker if you move away say twice the distance, right? The field will be smaller. So yeah, we could remember that. So we can put some power here. But anyhow, so let's say we only look at a circle of fixed radius, right? And then let's check that this is the accurate representation of vector fields. We take so that's the pattern that we expect. So at this point here, so when y is equal to 0, right, the vector field is directed upwards, right? So it's proportional. I'm only looking at sort of at this part now, right? So say this is point 1, 0, then vector goes this way, right? So and if we are at this point, then x is equal to 0. So the horizontal component should be equal to negative y, right? So it goes this direction, right? And then we go here and so on. So like at every yeah. So another reason to understand why this is true is that let's divide it by r, right? So we can write it in terms of sine and cosine. So in other words, the if say this is angle alpha, we can write so you'll have this vector here. We'll have components what's proportional to r times minus sine alpha cosine alpha, right? And that's exactly what you'll get if you apply the rotational matrix right to vector say 0, 1, right? So it will be it will show you how the vector rotates. Yeah. Anyhow, so that's right. So that gives you the magnetic field in magnetic field for the current that flows vertically. So you can also write it as it's proportional to negative y times vector I plus x times vector j. So what the power should be here? So how quickly the magnetic field decreases slower, right? So it should be it's 2 here, right? That's right. So that's another example of a vector field. And then of course there are more complicated examples, right? So say electric field from any electrostatic configuration of chargers or planes, magnetic field of a bunch of currents, field of velocity field of winds in the atmosphere, right? So pretty much as long as you can meaningfully assign a vector to every point in space, you have a vector field. That's right. Okay. Okay, so maybe we'll talk about one more example, which is so-called gradient fields. Right, and in fact, so one of them, what example of a gradient field already was the electric field, right? So electric field is equal to so Q divided by absolute value of x cube x, right? Now claim that E is equal to gradient of some function. And so can you tell us what this function is? So gradient vector field is a field such that there exists a function phi, which is a smooth differential function such that gradient field is equal to this field is equal to the gradient of that function. And so again, from that sort of question to reminder from physics, or we can just calculate it. What should be the function such that its gradient is equal to x divided by absolute value x cubed? That's right. Yeah, it's voltage, or rather electric potential. So voltage is electric potential multiplied by charge, right? So by the test charge that we put in the field. So how does this electric potential, what is it coordinate dependent? So in other words, which function you need to take a gradient of to get E? So I remind you that gradient is what it's like. So let's write it in components, right? So and then assume here that we live in 3 dimensions. So it's equal to Q over absolute value of this of R cube is what it's this function here, which is square root of, or rather, sorry, the yes, it's x squared plus y squared plus z squared to the power squared. Squared to the power 3/2, right? And components are x, y, z. So we want this to be gradient, right? So what is a gradient? Gradient is you could think of it as the differential operator, which is applied to every component, right? So it should be this, right? It should be phi x, phi y, and phi z, the derivative. It's a vector whose first component is x prime, right? And then and so on and so forth, right? So if you integrate that, right? So what will be so in other words, phi prime of x is equal to qx divided by x squared plus y squared plus z squared to the power 3/2. So let's integrate that, what phi is. Well, up to a constant, of course, right? Because potential and potential energy defined up to a constant. If you don't want to integrate, you can take the answer from physics and then just write it in these terms. Right, so if electric field decreases quadratically with distance, potential decreases as 1 over the distance, right? So let's write it in terms of absolute value of x. Okay, so and then how can you write it in terms of absolute values? So it's one, the denominator becomes power 1/2, and what's the, so it's what's right? So in other words, so if you integrate, right, so phi of x is equal to minus q divided by what? By absolute value x. Right? Yeah. So this is the well, there is also a constant, right, which you cannot. Well, because when you integrate here, it's a partial derivative thing. So once you do the integral, you have a function of x and y and z, but then you check it that it's the same in all directions. So therefore, if you take this phi to be like this, right? So phi to be equal to negative u over absolute value of x, then the gradient will give you this thing. And this is known as the electric potential. Okay. So electric field is a gradient field. Gravitational field is a gradient field. Formulae are literally the same, except we need to change some signs, right? So because electric force for the positive charge acting on the positive charge goes outside of the charge, and gravitational force is always attractive. Therefore, I need to put a minus here in the formula for the force. Okay. So electric field, gravitational fields, they have a potential, but does magnetic field have a potential? So can you do the same for, can you write that magnetic field B, say in previous example, is equal to gradient of something? Is that possible? Well, okay, we'll talk about this. Yeah, so it turns out that this is not possible. So magnetic field is not a potential field. It's not a gradient field. Excuse me. It's not a gradient field. Well, which is the same as potential in physics. It's not a gradient field. But you can do the next best thing. You can actually say that B is equal to the cross wall. There's an operation which we'll introduce soon. It's called curl. We'll have it later in the class. So it's curl. It's nabla across some function A. So there exists a vector field A, which is the vector potential, which is called such that it's if you take so there's this operation which is called curl. What you need to do, you need to formally do the cross product of this nabla symbol and this vector field, and as if you're calculating the cross product. And so it would look like this. It would look like you need to calculate the determinant in 3 dimensions, right? And which would give you the vector with components dy az minus dz ay, and this is dz ax minus dx az, and finally dx ay minus dy ax. right? So that the magnetic field actually becomes it is equal to this expression. So we'll talk about this in detail, but let me give you an example right now. So let's consider different configuration of the magnetic field. Say we have a circular current, right? So there's a current that flows in a loop over here, right? And then according to the right hand rule, the magnetic field will be pointed in the center of the solenoid of this loop, will be pointed upwards, right? So it will have it will look like 0, 0, and some scalar value b here. If you write it in x, y, z coordinates, it's a field that only has the z component. So therefore, if you want to find the vector potential A such that this happens, then this has to be equal to 0, this has to be equal to 0, and this has to be equal to, well, to this constant, right? And then we can try to find the vector function, try to find the vector potential A. So that this works, we can, for example, take it to be like this, right? So it's x. Oh no, sorry. dxay, right? So then, if you do it x minus y and 0 with coefficient b half, right? So then you get dx ay is equal to minus b half dy ax, sorry, not y minus, or plus b half is equal to b half, and dy ax is equal to also to b half, and all the others are equal to 0. And so if you do it this way, so with this choice of vector potential, you get a vector field that is vertical. Questions? Yeah. So that's another example of a vector field, which is not a gradient, but it's a field. It's a curl field. So that's what magnetic fields are. Yeah, curl isn't in 61. Curl will be in. It's a teaser, right? So curl will be later. We'll talk about curls in more detail. Sure. Okay, so let's make a quick break, and then we'll move on with integrals over curves. I'll see you soon. Okay, any questions so far? Now let's talk about integrals over curves. Integrals of over and we start off with integrals of functions over curves. So in the terminology of the previous hour, it will be scalar fields. So say you are given a function f Rn to R, right? And then there's a curve C which looks like this. There's a well, it does something here. Yeah, so say it starts from here and ends there. So just C of A, C of B. And then we can take a partition of element, sort of, our goal is to define an integral of a function f over curve C. We want to define this. Why? Well, first of all, why not? Well, and second of all, of course, like you can imagine, it's a useful thing to do, right? So it appears a lot in physics, in engineering applications. So if you take a partition of interval AB, and then image of this partition will be some partition of the corresponding arc of the curve. So yeah, so right, so the partition of this guy, as always, is a set of points like that, and then we have sort of 2 points, 2 neighboring points here. You can say C of Tn, Ci, C of Ti plus 1. So remember how we define the arc length in space. We would do the same, and then we would just integrate so it was an integral of just ds, right, over the curve, right? And then this ds was defined by, well, it was approximated as a limit when, you know, delta ti goes to 0, when the mesh of the partition went to 0, sum of delta si, right, where delta si is this distance over here. And so this delta si was, I remind you, because we know how to calculate distances in space, right? So, so it will be s, sorry. Let's say we're in 3 dimensions for simplicity. So it's xi minus xi plus 1 squared plus yi minus yi plus 1 squared plus zi minus zi plus 1 squared square root. And yeah, so we'll put it here, and then the this way we can calculate the arc length. And now we just the only modification of this procedure will be that not only we just sum the so if you have a finite difference, this way you're just going to calculate the sum the length of the curve, which is obtained by which is a piecewise linear curve, which is obtained by connecting those points. And when you do want to paste here the value of the function f, we want to multiply it by f of xi, xi, yi, zi. So, and then we do it for every point that we choose. So this way, as we send the mesh of the partition to 0, therefore by sending the number of those intervals to infinity, we would have defined the integral of function f over the curve, right? Because it only sums values, it only sort of takes into account values of the function that it takes on that curve, right? And then you would sort of it's a natural generalization of the Riemann integral. Only sort of now its support, it lives on this arc, right? It lives on the curve in 3 dimensions. And in fact, well, this procedure actually allows you to write it down, right? So in other words, integral of the curve is this thing, right? It's the, it will be, let's write it first as a Riemann integral, limit as n goes to infinity, sum of xi, yi, zi. I'm writing it for three dimensions, but of course it doesn't matter. You can do it for as many as you like. I goes from 1 to n delta si. Right. So that's the definition. But of course, in order to do some calculations, we want to be able to do it. We want to have a working formula in terms of explicit parameterizations of the curve, right? So say there's a parameter t that parameterizes the curve, then integral of a c of f will be the same as integral of f of a c of f of let's start again in 3 dimensions, x, y, s, x, y, z, ds. Or remembering that ds is equal to, well, I'm just going to write it here. I think by now we should be comfortable with the expression. So it's integral from a to b, right? F of x of t, y of t, z of t multiplied with square root of dx over dt squared plus dy over dt squared plus dz over dt squared dt. Right, so now it's an ordinary Riemann integral from a to b over the line, and then the fact that we're integrating over the curve is contained in the square root function here. Yeah. Let us do an example. The formula. So clearly it applies in 2 dimensions, in 3 dimensions, in any number of dimensions. So let's do a 2-dimensional example. So we want to integrate function 2 plus x squared y ds over the curve c, where c is the semicircle, upper semicircle like this. Minus 1, 1, 1. And then the integral goes, directional is also important, right? So it goes counterclockwise like this. So in order to even define the integral, we need to start off with describing this curve. So curve C will be a map from interval from 0 to pi, right, into R2, which is defined by the equations x equals cosine t, y is equal to sine t. And so as parameter t varies between 0 and pi, we'll get exactly what we want. And so let's call this integral I, and well, we can just compute it. So it's equal to 0, integral 0 to pi 2 plus cosine squared t sine t. And then, well, let's calculate the ds element here. So the distance, it will be root of x prime squared plus y prime squared dt. And of course, we know that it's equal to 1. Right? It's because it's a cosine and sine squared. Therefore, here there will be no additional fraction. There will be no additional square root factor, right? And it's sort of understandable, right? Because the sort of, in a sense, you can see the meaning of this square root is sort of, it tells you, it sort of describes you how sort of non-uniform the parametrization is, right? So it's essentially it's how quickly the point moves on the curve as opposed to as it moving on the line a to b. So here, what we're doing, we're simply stretching the interval from 0 to pi. So because we define it from 0 to pi, right? We know that the point moves with constant speed from this point to that point. So therefore, it's as if you are integrating over just a straight segment of length pi. Right? So that's why this factor is not is equal to 1. Okay. So let's do the integral. So we get 2 times pi from the first one, and then here we have integral cosine squared t d cosine t with a minus, right? And then cosine between 1 and 0 varies between, excuse me, cosine between 0 and pi varies between 1 and minus 1. So that equals what? That equals to 2/3. And this is the answer. Okay. Now, in definition of the integral, we assume that the curve, what exactly did we find the distance again? Do you mean this? Oh, it's just part of the formula. See, so that's what you need to calculate. You need to calculate integral of f of x of t, y of t, multiplied by the square root. And it just happens that in this example, square root is 1. So you would need to, we would multiply here by square root of what is it? Cosine squared plus sine squared, right? So it's cosine squared t plus sine squared t. Yeah. So now let's look at an example where it makes where it does make a difference, and we'll consider the so-called piecewise smooth curve. So in the definition, we assume that the curve C is smooth. That means it's differentiable, and there are no there are no critical points, right? But we can sort of make it a little bit weaker by saying that it's smooth only piecewise. So you should allow to have curves like with a like this, like with the sharp turns with spikes. So it's okay to for the curve as a function not to have a derivative at those things. So we can write this curve into components. Let's say if a curve is a union, I'm going to use the symbol here. So this dot simply means that we join the curves together, right? So if or another term, another word for this is concatenation, right? It's the same as in computer science. So if one curve is a concatenation of two or more curves, then you define integral of a function of a curve, right, as a sum of those integrals over two curves. Well, why this makes sense? Well, remember when you integrate something, when you do a Riemann integral, you can do the same thing, right? You could have a piecewise differentiable function, you can still define the integral. Like you wouldn't worry about one or two or 3 points. So they form what is called measure zero. So it does not affect the Riemann integral. Yeah. So let's do an example. Say the curve is given by a piece of parabola, and then there's a straight line, straight vertical line. So say this parabola is y equals x squared, and this is 0.11, and this is 0.12. So we're integrating like that. There are two components, C1 and C2. And exactly, so curve C is the concatenation of C1 and C2. So let's calculate integral over C of function 2x ds. Let's call it I. Yeah. So we need to break it into pieces, right? So it will be integral over C1 plus integral over C2. Let's parameterize those curves separately. So how do we do? How do we deal with C1? We can just have x to be a parameter, right? So we don't even have to call it. Well, if you wish, let's do x equals to t, just for uniformity, and y is equal to t squared, and that's what the parabola. That's what the parabola is. And then here t varies between 0 and 1. That's that. And curve C2 tells you that x is equal to just 1. Right? It's a constant. Everything happens at constant value of x. And y is equal to t. And now t varies between 1 and 2. So yeah, let's call this I1, and this we call I2. So I1 will be integral from 0 to 1, 2 times t, square root of derivative of x squared, which is 1, derivative of y squared is 4t squared dt. Yeah. So we call this u. And so du is equal to 8 t dt. And then when t is equal to 0, u is equal to 1. When t is equal to 1, u is equal to 5. So the integral gives integral from 1, I'm sorry. So we integrate from 1 to 5. So it's 1/4, right? So it's 1/4 u to the power 1/2 du. So that's u to the power 3/2, well, multiplied by 2/3, and then 1/4 from 1 to 5, right, which is equal to 1/6 of 5 to the power 3/2 minus 1. Okay, that's I1. And I2 equals integral from 1 to 2. Twice 2 times 1, x is equal to 1, multiplied by the derivative, so here it's 0, plus 1 dt. So it's equal to 2 times 2 minus 1, which is equal to 2. Right, so therefore, integral I is equal to 5 to the 3/2 minus 1 over 6 plus 2. Okay. Now, in some applications, it may be convenient to integrate over only sort of only integrate over x or only integrate over y. So, in other words, we can have what we want to do. We can integrate over the curve, and then we don't want to integrate over the whole length of the curve, but rather just integrate over x. So, or we want to do this over y. Right, so in this case, we won't need to multiply it by a square root. So then this integral will be equal to integral from a to b, f of x of t, y of t, x prime of t dt. Just for simplicity, I'm giving the example from 2 dimensions, and here it's a integral from a to b, f of x of t, y of t, y prime of t dt. So an example of this is calculation of center of mass. And so remember, so these guys, you can call them line integrals with respect to x and y. It's line integrals or curve integrals with respect to x and with respect to y. And so this is what they are. And a sort of practical application of this was calculation of the center of mass. Right, so say we have this, let's take another example of an arc. Only now it's an arc with variable density. So it looks like, so that it's getting thicker as you go lower, right? So it's the thickness of this thing grows as you go down. So it's a solid thing, right? So we have this, well, so it's a unit semicircle. And the density here and so the density is proportional to the distance to the line y equals 1. So is equal to some coefficient alpha times 1 minus y. And so the father, apart from so like you should think of it, so it's here at this point, it's like one point here, so it's thin, infinitely thin, and then as you approach y equals 0 line, you have the maximal density here. So the question is to find the center of mass of this thing, right? So from the symmetry considerations, it's more clear that it should be somewhere. It should be somewhere on the y-axis. So what we need to find, we'll only need to execute the integral over y. So we only need stuff like this, right? So I remind you the formula, right? So the center of mass was this coordinate of center of mass in the y direction was equal to 1 over the mass of the whole object. And then here we need to integrate over, well, in examples that we had, we integrated over a two-dimensional shape, but here it's a one-dimensional example. So we integrate over this curve. Let's call this curve C, which is the semicircle, the one we saw before. Y multiplied by rho of y. Well, technically it's rho of x and y, but it does not depend on x. ds. Right. And I think it should not. I'm sorry. This should not serve as a motivation for the line integrals with respect to x and y. So here we actually need to integrate. We're integrating over the whole s. Yeah. So we'll talk about the guys. We'll talk about the guys momentarily. Yeah. So we'll get. There it goes again. Put that on do not disturb as well. Give me 1 second. Okay, so let's find the center of mass of this shape. So we need to integrate over the curve the following function, right, which is y multiplied by rho of x minus y ds, and then which is equal to integral from 0 to pi. So remember, y was equal to sine t. And yeah, we'll also need to calculate the mass, right? So we'll do both integrals at the same time. So let's see, integral from 0 to pi sine t times alpha 1 minus sine t dt. That's the numerator. And the denominator will be the mass, which is just the integral of the density. It's integral from 0 to pi alpha 1 minus sine t dt. Let's try to do them both at the same time. So here we have, well, so alpha clearly cancels, right? There's no, it should not depend on this proportionality coefficient. And then the, yes, we have integral from 0 to pi sine t dt minus integral from 0 to pi sine squared t dt. And at the denominator, we get whole pi minus integral from 0 to pi the sign. Okay, now what these guys are equal to, this is equal to 2. And remember, it's the area under this arc of the sine function is equal to 2. Same as here. What's the value of integral sine squared dt from 0 to pi? Pi over 2. Yeah, that's right. So because it's 1/2, right? So it's 1 minus sine 2t half. So integral over sine 2t vanishes, so it's equal to pi half. So we get 2 minus pi half divided by pi minus 2. Right, which is, yes, is 4 minus pi minus 2, 1/2. So it's approximately, if you plug in the numbers, equal to 0.38. That's the position of the center of mass. Okay. Yeah. So now it gets back. Let's get back to the integrals with respect to x and y only. So yeah. So we basically what we're doing is simply ignoring the dependence on the other coordinate, right? And we sort of we're just integrating along the x-axis. So we'll literally define it as this integral, right? As if we did just multiplying the value of the function times the derivative of x prime only. So in sense, we're only looking at how the derivative changes in the x direction or in y direction. And then we can combine them together, right? So then we can have, for example, integral of a function, the f of xy, we can integrate it over dx. Then we can add to it integral. So because these guys are defined independently, then we can add to it integral over, say, some g of xy plus dy. Right. So the and yeah, so we can do the calculation here. Or we can write it as follows. We can write it as an integral over c, and then in the integrand we'll have two terms at the same time, right? So it's f of xy dx plus g of xy dy. So this integral here should be understood in the above sense, right? So you do, well, it's a linear operation, linear functional. So you first do integrate the first part, then you integrate the second part. Okay. So let's do an example on that. And it's more or less straightforward to just do the parametrization and do the calculation. So say we want to integrate over c y squared dx plus x dy, where curve c is a piece of parabola. So we'll just make a simple one. So let's say that it's a part of parabola between points -5,3 and 0.02. And the parabola here is x equals 4 minus y squared. Right. So here, so since this parabola is, and let's say the direction goes direction goes like this. keep the choice of the, actually, yeah, so maybe let's, for the sake of the argument, maybe let me flip the direction. Yeah, so direction will go this way. So we're integrating from this point to that point. Well, let's find the parameterization. So we can pick y as the argument now. So y is the parameter. This is curve C. Therefore, x is equal to 4 minus t squared, right? And then between which values t now varies? So it's -5 minus t, actually. I'm sorry, -5 minus t. So t changes therefore between, yeah, so it goes between -1 and -2, but sort of it goes in opposite direction, right? So, so -3 and 1, but we're integrating from 1 to -3. So therefore we have to multiply. We have to multiply by a minus sign. And so therefore that's equal to integral from, or we can just reflect it in the direction in the, so yes, like, so this is, this will be B, A, and this is B. So integral is equal to, integral is from 1 to -3, right? T squared dx. So if this is now dy is equal to dt, dx is equal to -2t dt. And then plus x, which is 4 minus t squared, dy, which is just dt. So that's it. That's the integral from 1 to -3. You have -2t cubed plus 4 minus t squared dt. And that gives us a -1/2 t to the 4th plus 4t minus 1/3 t cubed from 1 to -3. Yeah, so that's -1/2 times 81 plus a plus 1/2 minus 12 minus 4 minus 27 third, or plus 27 third, excuse me, and then minus, right? So minus 1/3, plus 1/3. Yeah. Well, need to simplify that, right? So not really into the mode of doing that. Anyhow, so that's equal to yes, yeah, so this one gives you what, -40. So it's not too bad, right? That's 28 thirds, and that's -16. So that's -56 plus 28 thirds. What? -168 plus 28 thirds minus 140 over 3. Why does it go from 1 to 3 instead of 2 to -3? Why 2? Oh, so we're integrating over y, right? So y changes between 1. So we have picked the direction. So the curve goes from this point like this to this point, and y changes between 1 and -3. What did I make a mistake again? Let's see. Oh, yeah, I think so. Yeah, sorry. I was copying it partly from the book, partly from my own. Yeah, it's 2 here. I'm sorry. Yeah, good point. I wish you told me earlier. Yes, okay, so that's 2 here. Also, we need to amend the calculation. Yes, I calculated the 0.01 does not belong to the curve. Yes, I'm sorry. Okay, then we need to change this a little bit. So it's to 2 then, right? So then, yeah. Okay, so half of this is wrong. So it's plus 8, right? So it's 16 over 2, and then it's minus 12 minus 8. And it's 27. Oh yes, plus 8/3. Yeah, now it looks okay. Well, yeah, not really. Oops, it's too much to delete. Okay, we can just remove it all here, and then we'll do the calculation on a different piece of paper, piece of the notes. Right, so yeah, so it's minus 81 over 2 plus 8, right? Minus 12 minus 8 plus 27/3, which is 9, plus 9, and then plus 8/3. Some cancellations here. It's equal to, well, 6. So it's minus 243 minus 3, right? So minus 18 plus 16. Yeah. So I got negative 245 over 6. That should look better now. Okay. Good. Yeah, thank you for that. Yes. So right, so basically it's you have to just be careful with the calculation. Good. And the last story for today is integrals of vector fields. Line integrals of vector fields. So now, we need to. So we talked about scalar fields, and now let's say we want to want to learn how to integrate a vector field over the curve. Say there's a curve like that. And since vector field is defined everywhere in space, in particular, it's defined everywhere on the curve, right? So for every point on the curve. So it does something like this. So you can think of the vector, this vector gliding so that its tail sort of glides along the curve. And the we need to sort of to combine together the notion of this of the curve itself and then the vector field. So what we can do, we can look at tangent lines for each point. We look at the tangent vectors. Right, and then we can compute the dot product, right? So here, say there's a point xi, yi. We have a vector field f. At xi, yi, and then there's a tangent vector t at that point xi, yi. And we define the integral as follows. So integral over f over curve C. So we take it we take the same definition. Only now we want to so the answer needs to be made a scalar function, right? So a number. So the integral should be a number, and then sort of the only way to make we need to make a number out of the vector field. So we need to take another vector field, right? And every curve likely provides us a vector field on its own. In fact, it should go in the examples from the above list. Take a curve and then study tangent vector in every point of that curve, like here. So this light blue vectors, and they also give you a vector field, right? Sort of only now sort of it gives you kind of its so I think in the first lecture I mentioned this. You can have a vector which is the constant vector field, but then you're going to also have this gliding vector. It's a vector whose tail sits at the curve at all times. So we can define it as follows. We have integral, we take a dot product of the vector with the tangent vector at every point. This way it's given, it is a scalar function, and then we integrate it over the curve. So this is the definition. So we define it like that because it's sort of the only meaningful way to make a number, well, positive or negative, depending on the computation, out of a vector field that lives on the curve. Okay. Now, from the previous studies, we know that the tangent vector at a point is the derivative of the radius of the radius vector at this point. So if you draw here radius vector of xi, yi, then the tangent, and then so we pick a parameterization for C. So again, so C is a curve which sends AB to Rn, R2 in this example. And we can rewrite this integral in terms of coordinate, in terms of explicit parameters. So this integral over C of vector field F is equal to integral from A to B. So it's F of, well, we consider like this is F of R of T dot with R prime of T dt. So yeah, that is the formula. Which define sort of which it's more or less the definition of the integral combined with the parametric with the parametric dependence. So maybe one more step of derivation is due here, because the way this goes, we can write it like this, right? So the reason why it's true is because you can write it as an integral from a to b, f of r of t, dot with, and now let's write tangent vector as the, so t, excuse me, so t, yes, t is the unit tangent vector. Yes, so it's r, sorry, I forgot to say that, right? So it's the unit tangent vector. And then, yeah, so you divide it by this, and then ds is equal to r prime dt. So in the week when we did the curves and curvature and stuff, we call this speed, right? We call this little v. So ds was equal to little v dt. It's the absolute value of r prime, and here we can multiply it here, absolute value of r prime of t dt. So this guy cancels, and we get the formula above. So sometimes people also write it like this. You can write it as integral from a to b f f dot dr, right? So dr of t, right? Because if you can denote this with dr, it's like it's the differential of the vector function. Okay. Good. Yeah. So that's it. I don't think we have time for an example, so I'll post the practice homework, and then we'll continue tomorrow. Are there any questions? Good. So then I'll see you guys tomorrow. Bye.